Welcome everyone to the ICTS monthly colloquium. It's a great pleasure to have Bhaswar Bhattacharya from the University of Pennsylvania give our monthly colloquium. Bhaskar got his PhD from the Department of Statistics in Stanford. And prior to that, he got his master's and his bachelor's degree from ISI Calcutta. I believe after his PhD, he spent a little time at Redmond working.
It was during my PhD.
Oh, it was during your PhD.
Yeah.
And then I think after that, he's been at UPenn since. So his area of interest include combinatorial probability, non-parametric statistics, inference on networks, as well as discrete and computational geometry. And today, you can see his title. He's going to tell us interesting things. Over to you, Bhaskar.
Thank you. Thank you, Vishal, for the introduction. Thank you for organizing this. It's a pleasure to be here. So I'm going to talk about motif estimation, polynomial chaos, and the Ising model. So these are three collections of problems at the intersection of statistics, probability, and statistical physics. They have very different backgrounds and different motivations, and might seem unrelated at first glance. But as we will see throughout this talk, there are some common themes, interesting common themes, which unify these topics. So here is a schematic outline for the rest of the talk. So I'm going to talk about three different problems, as I mentioned. The problem of motif estimation is sort of at the intersection of statistical inference and combinatorial probability. Then I'm going to talk a little bit about polynomial chaos, which is at the intersection of probability and statistical physics. And then, time permitting, I'm going to talk a little bit about fluctuations and inference in Ising models, which is at the intersection of statistics and statistical physics. So just, some fun comments about these pictures. This is just a picture of a network where we did some motif analysis. That one up there is the neighborhood graph of the United States. So if you can recognize, every vertex is a state. Two states are connected if they're neighbors. And we color every state red or blue, depending on whether that state went Democrat or Republican in the 2012 election. This was done years ago, almost 10 years ago. And we did some small Ising model fun simulations on that. I can tell you about that offline, but that's that picture. And this is Norbert Wiener, who started off the study of polynomial chaos expansions. Okay, so I'm going to start talking about the motif estimation problem, which connects in statistical inference with problems in combinatorial probability. So networks are a natural way to model relational data. If you have a group of people and they have binary interactions between them, a natural way to model them is through a graph. Now we know that the social networks that we see these days are huge in size. Social networks and contact networks are large. And so a key challenge that you face in network analysis is that the observed network is often a partial view of the total network. One never really sees the full network. You only see a small part of it. And this is often due to the size of the network, which makes it hard to search over the network or even store it or see it in any way. Sometimes it might be due to privacy or security reasons. So a challenge that you face as a network analyst is that you are seeing this network, which is part of a big network, and you want to estimate features of the large network by looking at these observed sampled network, subnetwork. So this line of work can be traced back to the early 70s by Coppo, Bianco, and Frank, who studied various objects about estimating the various functionals of the network based on sampling. So V. Frank is one of the pioneers in network science, and he wrote a series of papers on estimating the connected components of the big network based on an observed sampled subnetwork. And he also had several works on estimating what are called graph totals. This is just number of edges, okay? So studying small structures in a network like edges and triangles and wedges, this count of these local structures play a basic understanding of how the whole network behaves. And motifs are patterns of subgraphs in a network. So I'm going to have some pictures here and also fix some notation for the rest of the talk. An edge is just an edge. I denote it by K2 because it's a complete graph on two vertices. It's standard notation. The triangle is a complete graph on three vertices, so we call it K3. And a wedge is just one vertex connected to two neighbors, and that has a strange notation, K1, 2. It's the complete bipartite graph, one vertex on either side, two on the other. And so these are some basic motifs, and counting or estimating how many such motifs are there in a network based on an observed sampled graph is essentially the problem of motif estimation. And motifs go by many names. They are small graphs, so they are called graphlets. I mean, in combinatorics, they are just subgraphs, right? So here is the motif estimation problem. I have a motif H, a fixed shape, and I want to estimate the number of copies of H given a sample from a large parent graph Gn. Okay? So there has been, a series of work over the last several years trying to understand this problem. So there has been parallel line of work in computer science and in statistics, and the basic model is the same. You fix a sampling strategy, and you want to understand how quickly or how efficiently can you do the estimation. Now, of course, the more sophisticated your sampling scheme, the more efficient your estimator. But there is also a trade-off. The more sophisticated your scheme, what the kind of results you can prove, okay? So we will work with the very basic sampling scheme and try to get some precise results in that sampling scheme. So this is the first kind of sampling scheme you can think of, and this is called the subgraph sampling scheme. So you fix a sampling probability P, and you have your population graph V of Gn. You sample every vertex of the graph independently with probability P. And then you observe the graph on the set of sampled vertices. So here's the picture. Let's say this is the population graph. For every vertex, I toss a coin with probability P. If the coin comes up heads, I have a red there. And what I observe is the graph on the set of red vertices. So this is my population graph. That's my observed graph, right? Based on this graph, I want to understand features of this big graph. How many edges, triangles, connected components, things like that. Right? Okay. So the motif estimation problem, you fix a motif H, and here is a notation. So NH of Gn is the number of copies of H in the parent graph. I don't know this number because I don't know Gn. My goal is to estimate this number. So that's what I want to do based on the, yes, please. Exactly. No. So that's also done in a different sampling model, but not in this model. Exactly. Yeah. Right. So we will work just for the sake of simplicity and understanding what's happening throughout the talk. The running example will be to estimate the number of edges in the big graph. This is an easy problem. Edges is simple, but that's going to be a running example.
But in my edge, what's the right way to sample a subgraph?
Right. No. So Bernoulli sampling is not the best way. So there are other sampling where you sample a vertex and also you get to see all its neighbors. It's called one-step neighborhood sampling, things like that. So there are more sophisticated sampling schemes. But as I mentioned, the more sophisticated the scheme, the kind of results you hope to prove matters. Sometimes you can only get a rate. We will get extremely precise analysis. So it's a trade-off between what kind of thing you want to do and what's the actual. So I'll mention in the end other sampling schemes. Yeah, we understand what are better schemes, and there are some partial analysis in those other schemes. So we can do a random walk, which is a much better scheme in many ways, right? Right. Okay. So if you have an edge, you want to estimate the number of edges. This is a very easy problem. What you do is you count the number of edges in the observed graph. And when is an edge observed? An edge is observed precisely when both endpoints are sampled. So the probability of observing an edge is just p squared. So if you divide by p squared, that's the natural estimate, right? So the expected value of the number of edges in the observed graph divided by p squared is just the total number of edges in the population graph. Because each edge appears with probability p squared. So if you divide by p squared, you get an unbiased estimate, right? Yes, please. Right. Right. So that's a good point. So I'm going to do some asymptotics as the graph size grows. And the asymptotics is going to impose, for the asymptotics to be meaningful, it's going to impose some condition on the graph. So I, for instance, cannot take a full graph and an empty graph and a full graph like that. So a priori at this point is just to say that there is a graph whose vertex set is large. the results will then automatically impose certain conditions on the sequence of graphs. And we will show that natural models will satisfy those conditions. Right. Right. Okay, so that is a simple unbiased estimate, right? You take the number of edges in the observed graph, you just divide it by the probability of observing an edge. Linearity of expectation tells you this is unbiased. So just for some mathematical convenience that will be relevant later on in the talk, I'm going to write this in a somewhat algebraic manner. So the estimate n hat of the number of edges is 1 over p squared times this quadratic form, where aij is 1 if there is an edge in the population graph. This is an adjacency matrix of the population graph. And xi is 1 if the ith vertex is sampled. So this quantity here is only being counted if both I and j are 1 and that edge is observed, right? So this is a point to note that this is a quadratic form in Bernoulli random variables, okay? And so more generally, we can come up with an estimate, a very natural estimate for estimating any motif. So you fix a motif, let's say now a triangle. What's the chance a triangle is observed? All the 3 endpoints have to be observed. So the expected value of the number of copies that you see in the sample is p, power number of vertices, times the total number of copies, right? So if it's a triangle, p cubed times the total number of triangles. So if I just divide by that power of p, I got an estimate. No, so I'm going to count in the population graph is labeled, so I'm going to count that way. So there is a factor of automorphisms of h which will show up later, but yeah. So that is the most natural unbiased estimate of counting a motif h in the big graph Gn. You count the number in the observed graph and you divide by the probability that a motif is observed. This is such a simple model, yes, please. Right. Yes. Right. So then that case I will count like all the 3 edges or yeah. So this is just expectation, so the dependence is not captured here because everything is linear, so expectation still is correct. Yeah. There's no loops. There's no loops, no self loops, no multi-edges. Right. Right. Okay, so this takes the form of what in classical sample survey one calls a Horwitz-Thompson estimator. That's nothing. It's just well, in classical sample survey, when you divide by the probability of sampling a unit, what you get, you call it an HT estimator. So that's what we call that. So this estimator has been around for a long time, but it's only very recently that it has been shown that in a certain statistical sense, this estimator is best possible. So you can imagine in this model, what else could you have done? But it's only recently that it has been shown that this has the best variance among the class of graphs with a certain max degree constraint. So in a sense, this estimate is optimal. However, this result will not tell you that how can you do statistical inference with this. So what do I mean by that? In statistics, if you have a parameter, you get a point estimate, but you also want its uncertainty quantification. You want an error bar. To get an error bar, you need some kind of variance or distributional result. This will not give you that. So our goal here would be to come up with the asymptotic framework for consistency and finding confidence intervals. That's the goal, okay? So one has to first formally define what is consistency. So consistency means the estimate estimates the right quantity. And here we mean that the HT estimator is consistent if the estimate divided by the true value will converge to 1. That means it's estimating the right quantity. Now, to find out when is it consistent, to find some conditions on when it is consistent is easy. You just compute the variance. It will give you something. That's a basic concentration result. But we want to find sort of a right condition, a condition that is kind of tight. And to understand that, maybe it's helpful to come up with an example where this does not work, okay? So here is an example where the estimate will go terribly wrong. And this is going to be sort of our starting point of finding the right condition. So I take my population graph to be the n star, one vertex connected to n things. So this is a weird graph for this sampling scheme. Fix a sampling ratio of half. If you sample this vertex, then okay. If you sample this vertex, then you can see some neighbors. But suppose you do not sample this vertex, you get an empty graph. You did not sample this vertex, maybe you sampled some node leaves, but what does it matter? No edges got sampled. So if the central vertex is not sampled, the estimate is identically 0. So automatically, this result says it's inconsistent because it is 0 with probability half. I don't have to go any further, right? But if you do go any further and just do what it is, so if the central vertex is indeed sampled, then some number of leaves will be sampled. How many leaves are sampled? A binomial number of leaves are sampled. And if you do the computation, this ratio will be 0 with probability half and 2 with probability half. It's supposed to be 1, but it's nowhere, right? So it's not surprising. So for this kind of sampling scheme to work, this sort of suggests that I have to avoid having these kind of shapes a lot, right? So here is sort of the idea. Large degree vertices can cause the HT estimate to be too large or too small if they are present or absent in the sample. And to sort of get away from this issue, we need to ensure that the big degree vertices do not contribute too much. So here is the result. I mean, it's slightly technical, but it's kind of already summarized through that previous example. So this is a necessary sufficient condition for consistency. So we say that this estimate is going to be consistent if two conditions hold. The first one is saying that this parameter has to go to infinity. What is this object? This is the expectation of the number of edges in the sample. This is the expected number of edges in the sample. P squared times the total number of edges. That's the bare minimal you need. If something is consistent, you've got to see a lot of edge in the sample. If your original graph has 10 edges, your sample graph will have 2. How will it be consistent? So that's bare minimal. And that's the degree condition. And the degree condition is essentially saying, look at the large degree vertices, large properly defined. And the fraction of that compared to the total number is negligible. Okay? So the proportion of edges incident on high degree vertices is asymptotically negligible. So that's a condition which tells you that at least for estimating edges, what kind of graphs do you need to have? We have to avoid large number of high degree vertices. The number of high degree vertices should be controlled in certain sense. So this is only for edges, and I show it for the edges because it's more cleaner. But along similar lines, one can get a characterization of when the HT estimator is consistent for any motif. Okay, it's a similar principle. I'm not going to show the result, but it's kind of along the same lines. Right? So we understand, in a certain sense, that what kind of graphs we need to have for this sampling scheme to work. But this is only consistency. Remember, I want some uncertainty quantification, so understanding the variance of the distribution. Yes, please. Sure.
What does it mean? Because I could always construct specific large graphs with the sample get not characterization.
Right. Right.
So is there some change that if there's a measure in the set of all graphs, and with respect to that measure, these kinds of sampling techniques are optimal?
Right. So we are not showing optimality. Optimality is the previous result, but what we are saying, so these are some structural, these are all conditions on the population graph. These are some structural conditions on the population graph which need to be satisfied for the estimate to work.
I see. So let me consider following graph then, and you can tell me why this is wrong.
Right.
Let me just consider graph which have just this kind of mode, like the one that you showed previously. One central
Right.
That's not a high degree vertex.
Right.
That's just a 3 degree.
Right.
And can I have a disconnected graph where the whole graph is just copies of this kind?
Yes.
I can have that.
I can have
So
that.
then the correct estimate is that the total number of such motifs is the full number of vertices divided by 4. Because all 4 vertices are combined into 1 and or maybe in this case 5.
Okay.
So it's just multiple copies of it.
Right.
The correct estimate is total number of vertices divided by 5.
Right.
Of course, if I take a sample,
Right.
I'm not likely to, because there are many times I won't sample.
Right.
etc.
Right.
So it's hard to come up with that estimate.
Right.
Could you please explain where this is going wrong if the P to the B, for instance, is not given in a direct answer, which is A divided by this particular.
So the point is, you have how many stars do you have? If you have a large number of stars, then you are going to sample quite a few number of them, right? And that will automatically, that can give you a good estimator. So if you have, let's say 5 of them, then there is a problem. But if I have hundreds of them, I'm going to sample 50 of them, and then so there's a trade-off between the degree of that vertex and how many there are. And there is this trade-off, right? So of course, I mean, yeah.
So you're saying if I just scale up by p to the power 5,
Right.
That's enough to give me.
Yeah, so it's a delicate matter. It depends on the number of such stars. Yes, so yeah, something like that. Yeah. Okay. So it's an asymptotic design. Yeah, so yeah, right. So the real goal really is to find out some fluctuation results, some confidence interval type results for the estimator. And to do that, we first look at the estimate, we subtract the mean, we divide by standard deviation as we normally do, and I call the standardized object ZH of Gn. My goal is to understand when is this thing possibly Gaussian. If it is, I can get a confidence interval. So here is the result. And so let me try to parse this out for a moment. Parse this out. So I have a fixed motif H, and I have a population graph Gn. I have a technical assumption that the sampling rate is not too large. This is not that important, but sampling rates are usually taken small, otherwise there's no compression. So it's less than 1/20. Then the Wasserstein distance between the standardized statistics and the normal 0-1 distribution is bounded by the fourth moment of my standardized quantity and 3. What is special about 3? Right, so standard normal has 0 mean, variance is 1, third moment is 0, fourth moment is 3, right? So what this is saying, that this quantity will converge to normal whenever the fourth moment converges to 3. We need no other assumption because Z already has mean 0, variance 1 by construction. So all I need is the fourth moment to go to 3. That's all I need, okay? So note that the standard normal's fourth moment is 3. And what we have is what is called a fourth moment phenomena, that the statistic will converge to a standard normal whenever the fourth moment converges to 3. Okay, any questions? Yes, please. Yeah, so that is, so I'm going to explain to you later if you remind me in 5 minutes. So this is to get the fourth moment condition, and I'll tell you why. So the fourth moment has to be, we have to ensure the fourth moment is greater than equal to 3 somewhere. And there are finitely many values for which this fails. And I'm just taking the smallest value to get rid of this technicality. Yeah. So this is an example of what is called a fourth moment theorem. Okay.
Sorry, I had a question.
So we are using Stein's method, which is a technique for proving CLTs where the Wasserstein shows up naturally. It's not necessarily the right one, but it's the important point is that it's the fourth moment. But yeah, I mean, Wasserstein not necessarily, what would TV would be probably better, but Stein's method adapts to Wasserstein better. Yeah. Okay, so let me just take a little digression here to explain where does this condition come from and what does it mean, okay? So here's a little digression into the study of random multilinear forms, which I will come back to again in a moment. So let's suppose I have some IID normal random variables and begin with the random linear form. So it's a linear combination of normals. So a linear combination of normal is another normal, and we know what the variance is. So we know this quantity is going to converge to normal 0, 1 whenever that square of the i's will go to 1. There's nothing going on here. This is very simple. But let's now look at a random quadratic form or a random multilinear form. So this is what is called a Wiener chaos of order k. You have a k tensor A1 to AK. You sum over distinct indices, and you have Zi1, Zi2, Zik. This thing has mean 0 by construction because it's summing over distinct indices. If I compute the variance, it's just that. So let's, without loss of generality, assume that the variance is 1. I scale it out so that the variance is 1. So the question is, when is this thing normal, right? When is Qn asymptotically normal? So there is a very influential paper by David Nuallart and Giovanni Peccarti from 20 years ago, which says that this is normal if and only if the fourth moment of that quantity goes to 3. So this is the first occurrence of what is called the fourth moment phenomenon. Okay? Now, since the publication of this paper, the fourth moment phenomena has emerged as a general theme in determining normality of random multilinear forms. It's not just Gaussians. You can replace them with other variables, which just means zero, Rademacher variables, other variables, and somewhere you will get a fourth moment phenomena. That has emerged as a general theme, okay? So a few years after the publication of this paper, Ivan Nuruddin and Giovanni Piccardi combined Maliavian calculus with ideas of Stein's method to come up with what is known as the Maliavian-Stein calculus, which gives you quantitative rates for this convergence. And this is now a subject, okay? So Ivan Nuruddin maintains a website where he collects all papers that has the fourth moment theorem in it. Every year, there are hundreds of them. In December this year in Luxembourg, there is a conference to celebrate the 20 years of the fourth moment phenomena. So this is an industry now, okay? So as I mentioned, it is crucial in understanding central limit theorem of centered random variables. So you can take, plus minus ones here, what's called the Rademacher chaos, right? So where does the fourth moment theorem I just showed you fit into this general framework? So what we have, if you look at our estimators, if you look back at the estimate for edges, we have a random quadratic form in Bernoulli random variables, if you remember. If you write out it for any general motif, you have a multilinear polynomial in Bernoulli random variables. Not zero mean random variables, but Bernoulli random variables. So we have a Bernoulli chaos. So prior work in this area have only focused on Gaussians and Rademachers and zero mean random variables. What we have is a combinatorial sum, a multilinear polynomial in Bernoulli variables. So our fourth moment phenomena is a consequence of a general result. So look at this combinatorial sum. So this is sum over subsets of size R, ordered subsets of size R. You have a weight function, some non-negative weight function, times the product of xi over the subset. If R is 2, this is a random quadratic form in the Bernoullis, okay? It's a random multilinear form in Bernoulli variables. This thing, of course, does not have mean 0 because those are Bernoullis. So you center it and you divide it properly. And our fourth moment theorem is a consequence of a more general fourth moment theorem, which says that Bernoulli chaoses also have a fourth moment property. So this is not a surprise given the scale and the influence of the fourth moment condition, but every fourth moment theorem has to be proved separately, even though it's a unifying kind of thing. Right? And as I mentioned, this is very much in Stein's methods and adapts to the techniques of Stein's method. It's a technique for proving CLTs. So just to recall, how does our estimator fit in? That's the combinatorial sum in its generality. This one is the weight I choose. If I choose this weight, which is just the indicator that a subset has a copy of H, that solves the overcounting problem. And then this will converge to normal whenever the fourth moment goes to 3. And to answer your question about 1 over 20, the fourth moment theorem will fail for some finitely many values of P. So we have this root of the fourth moment equation you have to get rid of. So we assume 1 over 20. This is the Bernoulli case. Every fourth moment theorem has to be proved differently, but it will what you end up getting. That's the theme, right? Even for the Rademacher chaos, the fourth moment theorem is not true verbatim. You need a little assumption. In the Gaussian case, it's true verbatim. That's the only assumption. Yeah. Okay, so there are several questions which come here. First of all, remember our goal was to construct a confidence interval, get some uncertainty quantification. How does this result help? Well, this variance still depends on the population graph. So I got to estimate the variance somehow. That's the first one. More importantly, the fourth moment is a nice way to write an assumption, but it is hiding serious structural conditions on G. What does it hide? What kind of graphs will satisfy this condition? So that's the two questions going forward. So the first one is relatively simple. You can write down the expression of the variance and estimate it, kind of in a straightforward manner. What is satisfying is you need no other assumption other than the fourth moment. So you assume the fourth moment converges to 3. Then you have an estimate which is consistent. You have an estimate of the variance which is consistent. And you have an uncertainty interval. This is a statistical interval. This contains the true parameter with 95% confidence in an asymptotic sense. Okay? So here's a picture to show this work is working. I take a very simple example. The population graph is some Erdős-Rényi graph. I fix a sampling ratio of 0.03, and I do my interval 100 times. And you see a few of the intervals will miss the truth, a few of them will miss the truth, and it's supposed to be that. So 4 out of the 100 will miss. My alpha is set to 0.05. So empirically, about with 1,000 samples, I'm doing pretty well. Of course, I took a good graph here. That's of course I did that. Yeah.
The previous one, why did we have that max? You don't have to. Sigma square is always false.
The estimate might not be. So even though I put a square here, this is an estimate of sigma. This notation is confusing. This is always positive. But this square is confusing. But its estimate might not be. Its estimate might, so I truncate it to 0. I did write a square here because I'm estimating sigma squared by sigma squared hat. Sigma squared hat can possibly be negative. But so I make it nonetheless here. Right. Okay. So now to the second question of trying to understand what kind of graphs satisfy this condition. And I'm going to try to explain that, well, in the paper, we have several examples. I'm going to give 2 extreme examples here. So one is when you have a sequence of graphs with bounded degree. So if a sequence of graphs with bounded degree, then there is a threshold for the sampling ratio. Whenever the sampling ratio times the total number of copy diverges, you have a consistent estimate, otherwise not. So let me try to explain again where this is coming from. This is the expected number of copies. The expected number of copies that you see in the sample has to diverge. There's no hope of otherwise. So this can be a bad result because if there are not many copies, you need a large P. But that's unavoidable. If there are not many triangles in the big graph, how can I estimate it properly by sampling in an asymptotic sense? And so this is an effective sample size. And what this shows is this is necessary. So for sparse graph, we have the precise threshold which we need for consistent estimation. On the other extreme, let's think I have a dense graph. There are many interesting things happening in between. I'm not talking about it. Some of them are in the paper. But let's talk about the dense case, where a graph has n squared edges. So this is also a 30-second introduction to graphons, which is a terrible idea, I think. So if you have a sequence of dense graphs, there is a way in which you can take limits of those graphs, like you take limits of functions. And then you can write down a limiting graph in certain sense. And Lovász and others had this theory. It's not so important what a limit is, but you can, I think, possibly imagine that you have an adjacency matrix, which is a symmetric matrix. If you scale it down properly, the limit object will be a function on the unit squared, which is symmetric. That's all I need to know. So a sequence of matrices will converge to this symmetric function W, and the symmetric function will be an analog of a limit of a graph. And if you have a sequence converging to some function W, then in this case, if you have a positive density of that shape, your estimate's pretty good. Because a dense graph has many copies of subgraphs. So all I need is n times Pn to diverge. So I can take my sampling ratio as low as 1 over n almost, right? And then this is necessary. So this is 2 examples in the extreme to show when this estimate works and what kind of things you need on the sampling ratio for it to be a consistent and asymptotically normal estimator. Okay, so that's the end of the first part. Any questions? Yes. Yeah. Go ahead.
With the multiples that some theory has a sort of CI.
Right.
And you have the CIs for Gaussian.
Right.
How far can one push that?
Yeah.
Yeah. If the CIs were just 0 variance, 1 variables, how far can one push it?
This result is true for almost, okay, so you need the 4th moment plus some epsilon condition. That epsilon condition is specific to the choice of the distribution you take here, but it's a minor extra you need. You need a little condition, but the 4th moment is still true. So in the high level idea is this is true even if you replace the Gaussians by other things. It's not always if and only if. Yeah, so there's a little, in Gaussian it's if and only if. Yeah. No, like by epsilon I mean I need a little small condition. You had a question? Yes.
And we have these nice properties, consistency, etc. for sampling. Similar counterpart, you are trying to establish for the graph. There you have correlated parameters.
Right.
So the counterpart is that fourth moment phenomenon.
Right.
Now, my question is that what kinds of statistics, like you have this graphlets,
Right.
can I extend the similar result for the WL kernel kind of graphlets?
You mean W random kernels?
Weissman-Lemon.
Oh,
So you have
I see.
object which is like this is node, and then you have adjacent nodes.
Right. Yeah. I mean, possibly. Seems like that. I have to think about it, but possibly my short answer is possibly yes. Yeah.
And then another question is, what kind of degree distributions I can expect? So this results will be
Right. So estimating the degree distribution is slightly harder, but there are some results. This is not exactly inside our framework, but there are some results. It can be done. It's a little different, but yeah. Not directly, but you have some deviations you can do. Yeah. Okay. So let's do the second part, which is about polynomial chaos functions, which we already saw some of them here. So what are these objects? Okay, so fluctuations of the quadratic chaos. So in particular, we already saw like the class of multilinear forms, polynomial chaoses. So now in particular, I'm going to focus on the case of the quadratic chaos, where the polynomial has degree 2. So here is the setup. Now I am back to the setting of zero mean variables. I was in the Bernoulli setup, now I'm the zero mean setup. I have a bunch of random variables, zero mean variance 1, common distribution function if. Here is the F quadratic chaos. If F is Gaussian, Wiener chaos. If F is Rademacher, Rademacher chaos, right? This is a quadratic form. I'm going to assume that A is 0, 1 value. That's because, that's not necessary in some of the results, but that's largely needed for our analysis. So the question is, Tn has mean 0. So when does Sn, which is Tn over standard deviation, what is the asymptotic distribution of Tn over the standard deviation? So because I'm assuming that Aij, AUV is a 0, 1 valued matrix, in the back of my mind, I associate it with a graph G, which is the adjacency matrix associated with that. So this object Tn is a very basic object. It appears in various different fields. You open any book in asymptotic statistics, you see that. It's called a degenerative statistics. It appears as the Hamiltonian of the Ising model, which I will discuss in a moment. It appears in lots of statistical tests in time series literature. And it also appears in some extremal problems in combinatorics in the study of Ramsey theory. So understanding the asymptotics of this object is basic. And we know a lot about it. So for instance, combining some results about the fourth moment and some little gap in the literature which we filled out, this result shows that whenever the random variable xi has finite fourth moment, its normality is characterized by the fourth moment condition. So at least in the quadratic case, we have a precise answer. Doesn't have to be Gaussian. We only need finite fourth moment. We actually don't even need that, but that's a different story. Okay? So normality we know. When is this normal? We have a precise understanding. So the question is, can the limit be non-normal? Are there situations of graphs or some situations where I can take the matrix A, so the limit is not normal? And of course there are. Take Aij, AUV to be all one, the complete graph. That's an object you see in nearly every book in asymptotic statistics. Every book. That is a degenerative statistics. That object you can write down. This is summation xu xv. You just complete the squares with summation xu whole squared minus summation xu squared. Do a little CLT. That's a chi-square. Square of a normal minus 1. So we know very well that if you take the graph G to be the complete graph, then the limit will no longer be normal. That's well understood. Okay? And this phenomena extends to dense graphs. You don't really need to take a full complete graph, but you take a dense graph, this phenomena still holds. So here is a result from a few years ago. You take any graph Gn, any 0, 1 valued matrix, converging to a graphon, right? This graph one is this function. Then the limit will have two parts. There will be a Gaussian part, and there will be a non-Gaussian part, which will be a sum of centered chi-squares. Okay? These sigmas and taus are some constants, not so important. What's important is these are all normals. So that's a normal, and that's a chi-squared centered. And what are these lambdas? This graph one is a kernel, right? It's a symmetric function. It's a kernel. So there's it's an operator. So it's eigenvalues. The eigenvalues. If you look at that result, a complete graph corresponds to taking W equal to 1. Everything is 1. In that case, this sigma is 0. This sigma is 0, and it has only one eigenvalue, and you put things together, you get that. So we have a class of examples where the limit can have a non-Gaussian component given by a quadratic form, given by a centered chi-squared. Also, we have many examples where it's normal. So the question is, one can ask, what are the class of all limits of an F quadratic chaos? These are two classical limits. Are these all? Or can we get more? So we know that it can be a Gaussian or a weighted sum of chi-square or a combination of both. But can we get something else? So we were working on related problems for a long time, and we realized that it's possible to get a third type of limit. Okay? So here is the example. So take your matrix A, the 0, 1 valued matrix, to be the adjacency matrix of a complete bipartite graph with two vertex on one side and n on the other. Two vertex on one side and n on the other. It's a pretty simple example. Let's blast out a computation. So AUV is a complete bipartite graph with 2 on and 2n on one side, n on the other. So what is my random variable Sn? It is x1 times all of that plus x2 times all of that. So it's x1 plus x2 times the sum of the xi's. Standard deviation is like root n. CLT will make this sum go to normal. I have this x1 plus x2 hanging out here. This goes inside as that. So what I have is a normal distribution with a random variance. And the distribution of this object, if there are only 2 of them, or there can be 3 of them, this is depending on what f is going to be. This depends on what f is. So we have a third kind of limit, which is in a sense not universal, which depends on what f is going to be. Right? Yes. So again, this big degree. Whenever there are big degrees, this is going to come up, right? So this is a normal mixture where you mix on the variance, okay? So the result that we proved a few years ago was that if you look at Sn, which is Tn over standard deviation, these 3 are all the possible limits you can get. So you take Sn, you make, this is an informal statement because formal statement is hard to make here, make some appropriate assumptions so that the limits kind of exist. Then Sn is the sum of 3 components. First one, Q1, is a Gaussian. Fourth moment phenomena gives that. The last one, Q3, is this chi-square business. And the middle one is the normal with the random variance. And these 3 parts are independent. So any limit, the limit of Sn can be expressed as that, and any limit is of this form. So this assumption, appropriate assumptions, is not hiding anything fudgy. It's just ensuring things have limit, and whenever it has a limit, these assumptions are going to hold along subsequences. So this is a characterization theorem for the quadratic chaos. Right. So I have a I just took the slide out late last night. I have a proof by picture. so I'm going to show you the picture in the end. But what we do is essentially look at these 3 examples that we have. So we partition the set of vertices of Gn into 3 parts. Vertices which have very high degree, vertices which have medium degree, and vertices which have low degree. So this partitions the edge set into like 9 parts, 3 in between, like, in between and inside and inside. And then we just see what are the contributions. Very high to low is the normal mixture Q2. This part is going to give you the Gaussian and the normals. I'm going to show you the picture in the end. It's in the end. So it's basically looking at this example and just trying to partition the graph in a way that decouples these 3 parts of the graph. Yeah. So we need an assumption that the matrix is 0, 1 value. We believe it's true even without that assumption. We need that because we are doing, combinatorial counting in our estimate. There's a method of moments combinatorial counting somewhere, which is a technical requirement. Yes, the partition of vertices. Yeah. Yeah. Okay. So the high degree with high degree does not contribute because there are not too many vertices of high degree. You cannot have many vertices of high degree, so its contribution to the variance is negligible. So many of this is high degree to medium degree does not contribute because there are not many vertices. You cannot, if you have many vertices of high degree, if you have many, this will get you a normal again. This will average out. This will average out. So you cannot have many vertices of high degree. If you can, that goes in some other part. So very high degree is limited number. Limited number. Yeah. Okay, so that's the end of the second part, I think. Yes, second part is. Right. So that's a technical thing. I mean, so it's one of them is epsilon times square root of number of edges for some small epsilon. The other one is k times square root number of edges for some large k. So it's a technical thing. You need to look at the variance and do it here. Okay, so here's the third part. So this is about fluctuations and inference in the Ising model. Okay, so what is the Ising model? So it's a probability distribution over spin configurations. So we have a set of configurations, which is -1, 1 to the power of n. Each vertex, so this is the hypercube with 2 to the n elements. And the probability of any spin configuration sigma is given in this form. So it's a statistical physics model where the probability of sigma is exponential of beta times the term h and sigma. So beta is a parameter. We will take beta positive. It's called inverse temperature, or in statistics, the natural parameter. H and sigma is what's called the Hamiltonian. It takes a quadratic form, which is sigma transpose j sigma, which is that form. And j is the interaction matrix we will choose inappropriately. And z and beta is the normalizing constant that you have to make that thing into a probability. Okay? So in the Ising model, there's hundreds of things people study. So one kind of things that people look at is if you look at a sample from this Ising model and you look at observables like the Hamiltonian, look at the observable like the magnetization, you want to understand limit theorems for that. As n goes to infinity, what happens to these objects, right? So there's a long line of work here. So fluctuations of the partition function or the Hamiltonian or the magnetization are well known. There is a high temperature phase, there's a low temperature phase. I'm going to focus on the high temperature. It's somewhat easier to analyze the dependence. So here, if you take J to be the matrix of IID normals, this is the SK model. This is the Sherrington-Kirkpatrick model. So here, there is famous results of Eisenman, Lebowitz, and Ruel, which gives you the asymptotics of the partition function. So it tells you log partition function, which is a random variable because the Gaussians are there, has some limit, has a normal limit. The Hamiltonian was studied a few years later by Comets and Evu. In the Ising model case, the literature is more recent. So for instance, if you take the matrix J here to be the adjacency matrix of some random graph, then again, the Hamiltonian, the partition function are random variables, and properties of that you can study. So the thermodynamic properties were studied by Bouvier and Guillard, and the fluctuations of the partition functions more recent. So Dembo Montanari studied it in the case where the graph is locally tree-like, and then in the mean field regime where the degree diverges. This is Kabluchko, Lowe, and Schubart in a series of papers. You can also look at the random graph instead of an Edo-Shreni is some kind of configuration model coming from a power law. And so again, there is a long line of work there to understand fluctuations of these observables. Right? So what we are interested here is to sort of try to carry out this program, the program with the Ising model, instead of having an Edo-Shreni graph, having a inhomogeneous random graph, a graph coming from a graphon model, where every edge is not present with probability P, but with some probability that is inhomogeneous. So you fix the graph on W, which is a function, and what you do is you put an edge between two pairs I and J with probability theta n times Wi over nj over n. Okay? Theta n is a sparsity parameter. If theta n is 1, the graph is dense. If theta n goes to 0, the graph is sparse. So what do I have? I have the same model as before, where the j's are now generated by this random graph. So I have a random graph generated from this inhomogeneous model, and I look at now an Ising model on that, and that's what it is. Okay. So if you take all the W's to be same, you get a Doshrain. So first of all, let me try to connect and see what has this to do with the study of chaoses, and in particular the Rademacher chaos. So this is an easy observation that if you look at the Hamiltonian, you forget this term, this is a quadratic form. This is a quadratic form, sigma transpose A sigma. This is a quadratic form. Now, if you look at the parameter beta, and if you set it to be equal to 0, if you set that parameter equal to 0, that means every spin configuration is equally likely. This means all the spins are plus and minus ones with probability half. It's a Rademacher. So at 0, the Hamiltonian, the sigmas are plus minus ones with probability half, and the Hamiltonian is a Rademacher chaos. The Hamiltonian is a Rademacher chaos. And we have described the limiting distribution of that at 0. At 0 is just an independent model here in the previous work. Now the challenge here is to do it for positive beta, where you have dependence. So whenever you have a positive beta, these spins become dependent. So this becomes sort of a dependent Rademacher chaos, right? It makes much harder. So what is the distribution of the Hamiltonian in the case where you have a positive beta? That's a hard problem in general, because this becomes, the spins are dependent. So what people do is you assume some structure on A. Here in the previous result, I could do it for any A. So now I need to assume some structure on A. A-Shreni is a natural structure. What we do here is allow for an inhomogeneous random graph. So if inhomogeneous random graph, every edge is present independently with a certain probability. And I want to understand what is the fluctuations of the Hamiltonian. Okay? So here is the result. This is joint work with Shonchayan, this ongoing work, Shonchayan, Anirban, and Shomavo, two of our former students. So if you look at beta in the high temperature phase, so what is high temperature here? If you have Curie Weiss, or if you have the Edo-Shreni model, high temperature is 0 to 1. So here you have a graphon. The high temperature corresponds to 1 over the largest eigenvalue of that graphon. Okay? So in the full high temperature phase, you have the result that if you look at the Hamiltonian, then if theta is 1, which corresponds to a dense graph, then the limit has a normal component and it has a chi-square, a centered chi-square component. Remember that result with Sumit and Percy, which said, when beta is 0, we had something. This is for any positive beta in the high temperature phase. And then in the sparse regime, when you allow theta to go to 0, then the limit is normal. Okay? So this is giving you the fluctuations of the Hamiltonian in the entire high temperature phase. So this is a dependent Rademacher chaos with the underlying graph coming from an inhomogeneous model. So this is the high temperature phase, as I mentioned. And if I said beta is 0, this result follows from the previous result on graphons. That will follow from some fourth moment. None of that, of course, you can do here because things are not independent, but you can push it up to the full high temperature phase under the structure that the graph A is inhomogeneous random, right? Theta n is the sparsity parameter. So, right. So every edge is present theta n wi over ng over, right? Yeah. So it's not a dense graph. You can make it sparse. Yeah. Yeah. So that's a good point. So we can only allow into the -2/3. We think it will be much, much bigger than 1 over n should work, but that's a technical requirement. Bounded degree will never work because theta n is locally tree-like, and then the Hamiltonian will converge to something in that locally tree-like thing. So this is Dembo-Montanari. That's Dembo-Montanari, right? But this is supposed to cover the entire regime. We are not able to cover the whole regime, but that's just because the calculations are out of hand. But this is just a technicality. Yeah. Gn lambda by n, yeah. Yes. So there are results like that by others, and in other. So for the magnetization, which is the sum of the spins, there are results like that, where you don't have to take a random graph, but you can take a graph which is deterministic but approximately random. So for the linear functions of the spins, this has been established. For quadratic functions, not yet, but we expect these things to be largely universal. So I think it should be true, but we don't know yet. Yeah. Okay. So the last comment, to sort of wrap it up, is to sort of understand what this kind of results mean in the context of statistical estimation. So what is the statistical estimation question in the case of the Ising model? You have a configuration, you have a sample sigma. This is a spin sigma 1 to sigma n from the model P of beta. And the basic question is estimate beta. Look at the spins, estimate beta. So if you are a statistician, the first thing is you write down the MLE equation. That's the MLE equation. Maximize that with respect to beta. That's terribly hard because it involves Z and beta, which is intractable normalizing constant. So the way to get around it is to use what is called a maximum pseudo likelihood approach. I'm not going to explain what it is, but it's something to do with the conditional distributions. And it avoids computing this object. So Saurav Chatterjee pioneered the study of the MPL estimate in the case of spin glasses. A long time ago, we sort of found ways to find rates of estimation for the pseudo likelihood in generalizing models. But that's MLE, MPLE, whatever. The previous result that we just showed you has a way to estimate beta in the high temperature phase without going into any of that. How so? If you go back to this result, look at this result in the sparse case, there's a beta here, which means H and sigma actually converges to this object. So why don't I divide by this object on that side? This is just like an estimate of the number of edges. So there is a very simple estimate which is coming out of this Hamiltonian, surprisingly simple. No need to do any MLE, MPLE, nothing. So that's the estimate. Beta tilde is this estimate we just showed in the previous slide in the high temperature phase that is consistent. In fact, we have a CLT. In fact, we know this variance actually matches the variance of the MLE. So this simple estimator is actually, in a very strong sense, optimal. But it only works in the high temperature phase. Okay? But we get it out of it for free by doing the Hamiltonian's analysis. This, I think, is some one-step approximation of the MLE. To do the MLE, do some Taylor expansions, one-step approximation of the MLE, which somehow has the same variance. Yeah. Okay. So I'm going to show a picture to wrap things up. So this is the high temperature phase where the rate of estimation is root theta n. What happens in the low temperature phase? In the low temperature phase, we know from earlier work the rate is parametric, the rate is better. We don't know the fluctuations. We don't know distributions. So what happens is the estimate has a slower rate in the high temperature and a root n rate in the low temperature. And the phase transition is exactly at the point of the thermodynamic phase transition. So here's a picture to show that. So this is, we generate some Erdős-Rényi graph. I take my P to be n to the minus 1/3. P is theta, I'm sorry. So here, before beta less than 1, the rate is n to the 1/6. After beta 1, the rate is root n. So I plot the estimate and I plot its error bars. See, the error bars are much larger here because the rate is much smaller here. And suddenly the error bar becomes smaller and it's sharp at 1, like it happens, that's phase transitions, right? So exactly where the model undergoes phase transitions, the statistical rate of estimation also undergoes a phase transition from something slower to something which is parametric. Okay? All right. So I think that's sort of the end. I have a list of problems here. I mean, they are all here, but I don't think I need to go over it. But let me just say thank you. Yeah. Yeah.
I think we have time for questions.
I can show you the picture of the proof. Where is that? Here it is. That's the proof picture. So this is the picture of the proof. Yeah. That one. Anyway. Yeah, please.
Can you say something about the origin of this for someone who's not a probabilist or something, like the origin of this fourth moment phenomenon, like what is the intuitive picture behind why one expects this to happen in many situations?
Right. So, okay, so I can tell you the origin story, but I'm not totally sure okay, so let me see. The origin comes from the study of stochastic integrals. So if you have a function, if let's say it's a bivariate function, you can sort of try to look at, this function and, integrate it with respect to some Brownian motion, things like that. So this is basically, kind of what I'm talking about, these quadratic chaoses and stuff. So if you have a sequence of function fn, and you call that I of fn, you want to understand when this has a Gaussian distribution, things like that. And it's the study of these kind of stochastic integrals that led Giovanni Piccardi and David Nuala to come up with the fourth moment condition. Now, what this sort of is saying is that if you control the fourth moment of these combinatorial sums, you essentially control all other moments. In fact, a fourth moment is often equivalent to a 2k moment phenomena. You can write a similar statement like the sixth moment will converge. 4 is not special. You can do a sixth moment theorem. You can do an eighth moment theorem and things like that. And in sort of the case of the combinatorial case, for instance, so let's see. Let's see if f is plus minus 1. The fourth moment condition, you can write it out explicitly. It turns out to be related to the number of 4 cycles in the graph, because it has 4 edges, a fourth moment, 4 edges. And it's the fourth moment, the 4 cycle divided by the total number of maximum 4 cycles will go to 0. So it imposes certain structural restriction on the graph, and the fourth moment controls every other cycle. The other connection that is tangentially related is what is called quasi-random graphs, right? So if you have a graph whose edge density is p squared for some p, and a graph whose 4-cycle density is p to the 4, the graph is actually an Edo-Shreni graph. So somehow a 4th cycle characterizes all other motifs. A fourth moment characterizes all other motifs. But again, it's not special about 4. You can do it for every even moment. Yeah.
All right. If not, let's thank our speaker again for a wonderful talk.